Hello everyone, we're going to solve this redox problem. I'm going to read out the question before we start working out the answer to this problem. So in this problem, it says E naught for the following half reactions are given below. Zinc 2 plus 2 electrons going to zinc. E naught value is negative 0.76 volts. Aluminum 3 plus aqueous plus 3 electrons going to aluminum solid. E naught is negative 1.66 volts. And it says if zinc 2 plus aqueous, zinc solid, aluminum 3 plus aqueous, aluminum solid were all present in a solution. Write down the overall chemical reaction for the spontaneous reaction. Also calculate the net potential, standard free energy, and the KEQ for the overall reaction. Okay, so these are the problems. So there are four things to figure out. First thing we need to figure out is the overall reaction. What's the overall reaction? And write it in the direction in which it's going to be spontaneous. And then we're going to figure out the net potential, then the standard free energy change, and then the last thing we're going to figure out is the KQ. Okay, so let's get started with the first step, which is to figure out the overall reaction for this particular redox problem. Okay, so first thing is you have to analyze the two reactions and then figure out which one has the more positive reduction potential. And if you analyze it, you can see that the top reaction has a much more positive reduction potential. So we just write that down. So the first reaction is more positive, the second reaction is less positive. So if the first reaction is more positive, that tells you that that's the reaction that is going to undergo reduction. And the second reaction that we have is going to undergo oxidation. So once we have decided that the first one is going to undergo reduction, and then the second reaction is going to undergo oxidation, then we have to flip the second equation and then write it as the oxidation reaction, keeping the first reaction as it is. So the first reaction stays as it is. The second reaction has been flipped. And you can see that when you flip the reaction, we also have to change the sign for the E naught. So here it was negative. In step 2, it's now changed into a positive value because that's the oxidation reaction. Okay. And then in the next step, what we're going to do is that take these two reactions and then make sure that the number of electrons in both the reactions are equal. So the first reaction, if you see, it is working on 2 electrons. The second reaction is working on 3 electrons. Whenever there is an oxidation reduction reaction, equal number of electrons have to be lost or given up from oxidation, and then an equal number of electrons have to be taken up from the reduction reaction. So you can't have an uneven number of electrons. So how do we make sure that these two are equal? So we're going to multiply our first equation, which has 2 electrons, by 3, so that 3 times 2 gives us 6. And then we're going to multiply the whole second equation by 2, so that the 3 electrons, 2 times 3 is going to give us 6. But even though we are multiplying the equations, we should not multiply the voltages. Okay, multiply. So here, as it says here, multiply the equations, but not the E naught values. The E naught values are going to stay as they are, because no matter how many stoichiometric times, that is, whether you multiply something by 2 or 3 or 4, the voltage output that's going to come out from those reactions are going to be exactly the same. It's not going to change. It's not going to be twice the value or 3 times the value. That's not going to change. So your E naught is going to be the same exact value that you get every single time you run that reaction. Okay, so your E naught is going to stay the same. Now we just write it out after multiplying it, and when you multiply and write it out, so this is the new version of the equation. You can see that everything, all the numbers have been multiplied to all of the terms. Now we have 6 electrons on the top equation and also 6 electrons in the bottom equation. So we made sure that the electrons are balanced. Now that we've done this, then all we're going to do is go ahead and add the two reactions. And when you add the two reactions, because we have 6 electrons on this side and 6 electrons on this side, we can cross them out. We don't need to include them in the overall reaction over here. And then we just add up these two voltages, and then you're going to get the delta E naught value of 0.90 volts. And we call this delta E naught value as the net potential of the reaction. So we have, in going through these steps, we have figured out 2 out of the 4 things that we were asked to calculate in this problem. So first thing that we have done is overall chemical reaction for the spontaneous reaction, which we've already done. And then by doing this addition step, we've actually calculated the net potential. Whenever it says net potential, what it's referring to is delta E naught, because this is the non-biochemical reaction. If it's a biochemical reaction, we would call this delta E naught prime, but because this is not a biochemical reaction, we are calling this delta E naught. Okay, so this is the net potential for the reaction. So there's two more things to do. We need to figure out the standard free energy change and the KQ for the reaction. So first thing we're going to do is calculate the delta G naught. The standard free energy change is basically your delta G naught, and we're going to figure out the delta G naught value. And how do we figure out the delta G naught value? If you remember our previous calculations, in the previous calculation, delta G naught is given as negative NF times delta E naught, and where N is the number of electrons and F is the Faraday's constant. We just plug in the numbers. We already figured out our delta E naught, so we're going to take the delta E naught value and plug it in right over here. Okay, so when we do that, we're going to get the N value. If you remember, the number of electrons that we use to balance the two reactions is 6. Therefore, N becomes 6. Then you have 96,485 for the constant, which came from here. And then the delta E naught, the 0.90 volts came from here. So you multiply all of them together, then that gives you a delta G naught value of, negative 521019 joules per mole, or you can, if you want to report it in kilojoules, it's negative 521 kilojoules per mole. Okay, so we've gotten the delta G naught, and one comment that we can make here is that this is going to be a spontaneous reaction because our delta G naught is less than 0. So this reaction is going to be a spontaneous reaction. If you remember, the goal of the question was we need to write the reaction in such a way that our reaction is spontaneous. Now, using the delta G naught value, we have also confirmed that the way we have set up everything is correct, because the delta G naught value that you've gotten is actually negative, and therefore our reaction is spontaneous. Okay, so that's an important point to note here. All right, so now we're going to calculate the KQ value. If you want to calculate the KQ value, we're going to exploit a thermodynamic relationship that connects delta G naught to KQ. And that equation is delta G naught equals negative RT ln KQ. And if you remember, R was our gas constant. Because we were working with energies, the R value is going to be 8.314 joules per Kelvin times mole. So that's going to be the R value. And then for this calculation, we're just going to use T equals 25 degrees Celsius or 298 Kelvin. So we're going to use that for our calculation. Okay. So, but our goal is to find out what is the value of KQ. Okay. So we want to get the KQ. So we have to do a little bit of math to rearrange all this stuff. So what I'm doing here is, I'm getting rid of the RT on this side of the equation. So that means I'm dividing both sides by negative RT. When you divide this side by negative RT and this side also by negative RT, we're going to end up with ln KQ is equal to negative delta G naught over RT. Okay, so this is what we're going to end up with. So once you end up with ln KQ is equal to negative delta G naught over RT, we have to get rid of this ln, because we want only KQ, we don't need the ln there. So if you want to get rid of ln, the best way to do it is raise both sides of the equation to the power of e. So if you raise both sides to the power of e, then we can get rid of the ln. So how does that look like? So if we are writing it as e to the power ln of KQ, this whole thing on the top of e, and then this whole thing also on top of e. So e to the power negative delta G naught over RT. So everything is raised to the top of the e, and once you do that, this e and the ln are going to cancel each other, because taking the ln natural log of something and then raising it to the power of e are opposite operations, so they cancel each other out. So the final equation that you're going to end up with is KQ equals e to the power negative delta G naught over RT. Okay, this is the equation that we need, because all we are trying to figure out in this process is KEQ. So if you want to figure out the KQ, we just plug in our delta E naught that we figured out in the previous step. We know the value of R, we know the value of T, we just need to plug them in and then solve for KQ. So how does that look like? So we know that our delta G naught is these many joules per mole. I'm using the delta G naught in joules per mole as the unit because the R value that we're using in this equation has units 8.314 joules per Kelvin times mole. So because both of them have joules, so I want to make sure that this delta G naught also has units of joules. Okay, so that's the reason why I'm writing it out in joules per mole. So we set it up, we plug it in there, and then we simplify that equation, and we can see that the units actually cancel out. See, joules cross out, moles cross out, Kelvin cross out. So that means there's going to be no units on top of the exponent. And we're eventually, when you simplify this fraction that we have here, this whole thing over here simplifies to this 210.29. An important thing to pay attention to is see that our delta G naught has a negative sign here. and then there's a negative sign also on the outside of it. So that means negative times a negative is going to be a positive value. So one of the common mistakes that happens is when you are setting this up, you forget that the delta G naught has a negative sign in the front in the equation itself. So if you miss that, then you're going to end up making mistake with the math that is involved in it. And the second type of mistake that happens is that when you're setting up this fraction, which is 52109 divided by 8.314 times 298, it is better that when you're doing the fraction in your calculator, put the bottom part, the 8.314 times 298 within brackets, because sometimes when you put it the wrong way in your calculator, then it's going to give you an incorrect value. So make sure that 8.314 times 298 is actually within brackets when you put it in your calculator, and then that's going to give you this 210.29. And if you take the e to the power of 210.29, then it gives you 2 times 10 to the power of 91. This is a huge number. So that tells you that your KQ is very, very large, very large. So what does KQ mean? KQ is the equilibrium constant. And the equilibrium constant is written as products over reactants. That is the product concentrations over reactant concentrations. And when your product concentrations are very, very high compared to reactant concentration, your KQ value is going to be really, really large. So in this case, in this problem, our KQ value is a very large number, 10 to the power of 91. That's a huge number. So this large value of KQ tells you that in your reaction, you're going to have a lot more products compared to reactants. Therefore, your reaction is going to be very, very product favored. That means you're going to make a lot more products compared to reactant. That means the reaction is going to go completely in one direction, not in the other direction. So your overall reaction is going to be more product favored. So that's what this is saying.